Let's talk about floating point data and x86. There are three different floating point data types that the processor recognizes and operates on. One is the data in single precision format, which is otherwise known as the float data type. The double precision format, known as the double data type, and the double extended precision format, which is known as the long double data type. Float occupies 4 bytes in memory, double occupies 8 bytes, and long double occupies 10 bytes. These formats directly map to the IEEE floating point standard. Now let's take a closer look at the single precision format. The single precision format, as I said before, occupies 4 bytes. Bit 31 is the sign bit, which is the most significant bit. The next 8 bits form the exponent, and the lower 23 bits form the mantissa in the single precision format. The interesting thing about the exponent is the format saves not the real exponent but a biased exponent, and the biased exponent can be calculated by adding a biasing constant to the real exponent. The biasing constant for single precision format is 127. Now let's take a floating point number and try to convert that into a single precision format. And we'll try to verify our answer by a simple C++ program towards the end. So we start off with a floating point number, which is 10.25. The first step is to convert that to binary, and we get 1010.01. And once we have converted that to binary, the next step is to normalize the number. And by normalization, we simply mean to move the decimal point 3 places to the left in this case and adjust the exponent accordingly. So the resulting number is of the form 1.01001, and the exponent has been adjusted, and the new exponent is 3. We then can extract the mantissa, which is 01001, and that's the number to the right of the decimal point. The integer 1 to the left of the decimal point is implied and it's not saved explicitly. And that's the whole idea behind normalizing. All floating point numbers will have a 1 point in the integer portion, and they don't need to be saved explicitly. The real exponent in this case is a 3. And as we mentioned before, the value that is saved for the exponent in the format is not a real exponent but a biased exponent. So in this case, we save a biased exponent of 130 after adding 127 to the real exponent. The sign bit in this case is going to be a 0 since we are dealing with a positive number. Now let's try to plug in all those values that we extracted in the previous slide. So the sign bit is a 0 since we are dealing with a positive number. The exponent that we calculated was 130, which was a hex 82, which in binary is 10000010. And the mantissa is 01001, and the rest of the mantissa is padded with zeros. So in hexadecimal format, this single precision number looks like 4124 followed by 4 zeros. Now let's try to verify if our calculations are accurate. So what I'm going to do here in the editor is create a union, and one of the members is going to be float, and the other member is going to be an unsigned int, and I'm going to call it single precision, single P for short. So once I have this ready, I'm going to set the floating point fnum to equal 10.25, which was the number that we started out with. And then to display the single precision, I simply print the single P, which is the single precision member of the union. So I just do, I'll add a 0x for better readability, and then I just do an f dot single underscore P. So this should display the single precision value of this floating point number 10.25. So let's run this, and you can see that this matches the calculation that we did in the earlier part of the video. Now if I was to replace this number, instead of a positive number, if I was to change this to a negative number, the only change I would observe is in the sign bit, which is the most significant bit. So I would expect a value of C, a value that starts with a C, and the rest of the number is going to stay unchanged. And this shows that the most significant bit, which is in the single precision format, is a 1 in this case, since we are dealing with a negative floating point number. I hope this video was useful in understanding the single precision format. I'll see you guys in the next video.